Tomorrow, research teams will finally release a set of high-resolution images that remained unavailable for more than 40 days. Before these materials become public, it is important to understand the context surrounding their delayed publication. Over the past weeks, several scientific groups emphasized their commitment to transparency and rapid data sharing, repeating the idea that information would be released as soon as it was obtained. Their messaging was consistent, polished, and clearly aimed at reinforcing trust. However, the technical reality did not match these assurances. The high-resolution imagery of the object, designated 3I Atlas, taken from a distance of roughly 29 million kilometers, with a scale of about 30 kilometers per pixel, was withheld for 43 days. This delay prevented independent analysts from evaluating the object during a crucial window. Ground-based telescopes lost the opportunity to observe several key segments of its trajectory, and international collaboration stalled while researchers waited for data that had already been collected but not published. During this period, early commentaries appeared online, shaping the perception of 3I Atlas as a routine long-period comet with no unusual properties. These narratives circulated widely, even though observers had already noted several inconsistencies. For instance, the object displayed directional outgassing both away from the Sun and toward it, a behavior that cannot be explained by standard solar-driven sublimation. Additional spectral deviations were recorded, and the trajectory of 3I Atlas lay almost perfectly within the plane of the ecliptic. The probability of an interstellar object entering the solar system along such an aligned approach is extremely low, estimated at a fraction of 1%. This alignment alone does not define the object's nature, but it does raise questions about the assumptions made by astronomers who immediately categorized it as typical. Combined with the unusual outgassing patterns and chemical irregularities, the data suggested a more complex profile than the early public statements implied. A second layer of complexity emerged when observers noticed that 3I Atlas maintained structural stability over long intervals, despite moving through regions of the solar system where thermal stresses should have affected its surface. Small fluctuations were present, but the consistent shape retention contradicted expectations for fragile, icy cometary bodies. Normally, outbursts, fragmentation, or shedding events occur as comets heat unevenly. In this case, the object preserved a coherent form while still producing narrow, highly directional emission plumes. These plumes were particularly noteworthy. Instead of broad, diffuse releases typical for volatile-rich nuclei, the emissions of 3I Atlas formed thin, stable jets with minimal dispersion. Their directional consistency hinted at a more rigid internal structure, or at least at material properties not commonly observed in primitive small bodies. Throughout this period, cosmic investigators did not offer detailed explanations for the plume geometry. Public comments focused on generalities about heterogeneous surface regions, or localized heating, but these remarks did not align with the measured vectors of the observed jets. Several independent astronomers noted that the plumes emerged at angles inconsistent with solar heating gradients, an observation that never appeared in the official summaries. When the first mid-resolution images leaked through secondary channels, analysts pointed out another anomaly: the apparent lack of a classic coma. Instead of a diffuse envelope of gas and dust, 3I Atlas produced only faint, tightly bound material traces. This characteristic placed it closer to asteroidal objects than cometary ones, yet its emission behavior remained comet-like. The combination produced a profile that did not fit cleanly into any existing category. These inconsistencies accumulated. Trajectory alignment, minimized coma, directional plumes, and spectral irregularities all pointed to the same conclusion. The object was not behaving like a typical interstellar comet. Despite this, early statements continued to describe it as entirely conventional, with no indication that more complex interpretations were being considered. Analysts who compared the official commentary with the observational record noticed gaps, unanswered questions, and a notable reluctance among scientific groups to address the irregular data directly. With the upcoming release of high-resolution images, the situation may finally change. These images could clarify several unresolved points: surface structure, rotational behavior, jet origins, and the physical mechanisms driving the emissions. The delay in their publication remains unexplained, but once the images become available, a more accurate assessment of 3I Atlas will be possible. Until then, the discrepancies between observational data and public statements continue to draw attention, especially among researchers who track deviations from established models of interstellar objects. The upcoming high-resolution images are expected to clarify whether 3I Atlas shows signs of surface irregularities, asymmetrical erosion, or subtle fragmentation events that were not visible in earlier datasets. These details matter because the observational record already contains several points that challenge the early conventional descriptions offered by astronomers. Once the new images are available, independent analysts will be able to re-evaluate assumptions that have been repeated for weeks without direct evidence. Research teams have emphasized that their communication strategy remains neutral and strictly data-driven. Yet their approach has shown a consistent pattern, presenting interpretations before releasing the underlying measurements. While this may streamline public engagement, it also creates a situation in which conclusions precede verification. Analysts following the case expected a more cautious stance, one that acknowledged uncertainties, highlighted unresolved dynamics, and avoided establishing definitive narratives in advance. This pattern was especially clear in the way the object's rotational behavior was discussed. Early statements framed the rotation of 3I Atlas as stable and typical, though the photometric data available to independent observers indicated periodic fluctuations inconsistent with a simple spin model. A standard tumbling motion could have explained these deviations, but the observed light curves displayed irregular peaks that did not match known profiles of multi-axis rotation. These details were never addressed in official commentaries, which continued describing the rotation as normal without elaboration. Another unresolved issue involved the thermal distribution across the object's surface. Scientists mentioned that heating patterns were predictable, yet the infrared readings reported by several observatories showed localized hotspots that persisted even when the object moved further from the sun. This persistence contradicts the usual thermal behavior of volatile rich bodies, which normally cool rapidly as insolation decreases. Several analysts suggested that the thermal inertia of 3I Atlas must be unusually high, implying a denser or more coherent internal composition than expected for fragile interstellar debris. Despite these discrepancies, research groups maintained a consistent narrative. The object's behavior, while interesting, was fundamentally unremarkable. The lack of detailed clarifications led many observers to conclude that the official summaries emphasized normalcy while leaving out the elements that did not align with established cometary models. The release of the new images may indicate that the research teams are now prepared to address these irregular data points more directly. Another important aspect centers on the object's approach trajectory. While astronomers acknowledged that the alignment with the ecliptic plane was statistically unlikely for an interstellar object, they described it as a coincidence requiring no special explanation. Independent analysts disagreed, pointing out that such an alignment implies a very specific incident angle, one that would require precise entry conditions for an object originating outside the solar system. Though coincidence remains a possibility, the probability is low enough to justify a more detailed examination than what has been presented so far. The object's velocity also raised questions. Initial estimates indicated that 3I Atlas was moving slightly slower than typical interstellar objects detected to date. Such velocity could indicate prolonged deceleration processes, interactions with interstellar dust, or gravitational influences encountered during its journey. Yet none of these possibilities were explored in public statements. Research teams instead focused on generic explanations, describing the velocity as within acceptable ranges, without referencing the statistical deviations that independent analysts highlighted. In addition, observers noted an unusual consistency in the object's albedo. Comets often exhibit significant brightness variations due to uneven surface features, dust release, and rotational dynamics. In contrast, 3I Atlas maintained a remarkably stable reflectivity over extended intervals. This stability suggested a surface composition or structure not commonly associated with small icy bodies. Despite this, no detailed analysis of reflectivity patterns was released, and official summaries simply referred to the object's brightness as steady. These unresolved elements created growing interest among researchers who specialize in anomalous small body dynamics. They recognize that none of the individual deviations were extraordinary on their own, but the combination of low coma density, directional plumes, thermal inconsistencies, rotational anomalies, and trajectory alignment formed a profile that did not match standard cometary classifications. As more data appears, analysts hope the research teams will address these combined factors with a level of detail not present in earlier communications. With the impending release of higher quality visuals, this may be the first opportunity to evaluate the true surface characteristics of 3I Atlas. The new images could confirm whether the object has a fractured crust, hardened mantle regions, or layered strata that would support the hypothesis of a dense, rigid interior. They may also reveal whether the emission plumes originate from discrete vents or from structural features that have not been observed before in interstellar visitors. For now, the scientific community is preparing for a shift in understanding. Once high-resolution imagery becomes available, previous assumptions may have to be revised, especially if the object continues to demonstrate properties inconsistent with conventional models. The next phase of analysis will depend on the clarity, completeness, and depth of the visual data that has been withheld until now. One of the most unexpected features recorded around 3I Atlas was the presence of sunward-directed material flow. Under typical conditions, dust and gas released from a small icy body accelerate away from the sun due to radiation pressure. This outward force is so dominant that a reversal of direction is considered extremely unlikely without an external mechanism. Yet observers documented streams of material moving toward the sun, a behavior incompatible with known physical models of cometary outgassing. To explain this anomaly, some astronomers suggested that the emissions may have originated from regions shielded from direct sunlight, allowing gas to escape in directions that coincidentally appeared sunward from certain viewing angles. However, this hypothesis does not align with the recorded trajectories of the plumes, which maintained stable sunward orientation over extended periods. The consistency of these vectors indicates that the effect was not a viewing illusion, but a genuine directional movement. Compounding the mystery, 3I Atlas exhibited unusually tight collimation of its emission jets. Unlike broad diffuse plumes typically generated by sublimating ices, the observed streams maintained narrow, coherent paths with minimal dispersion. Such structured emissions imply precise venting mechanisms or a more consolidated surface composition than what is normally seen in primitive small bodies. These characteristics prompted analysts to revisit the object's classification. Early reports insisted that 3I Atlas was a standard long-period comet, despite mounting evidence to the contrary. Independent specialists pointed out that the combination of sunward outflows, minimal coma, and high jet coherence had no clear precedent in documented cometary activity. Another area of scrutiny involved the object's approach geometry. 3I Atlas entered the solar system along a trajectory almost perfectly aligned with the ecliptic plane. For an interstellar object originating from random galactic directions, the chance of intersecting the solar system with such precision is extraordinarily low. Statistical studies estimate the likelihood at approximately 1 in 20,000. While improbable events do occur, the degree of alignment is significant enough to merit closer examination, particularly when combined with the other irregularities. Astronomers address this by suggesting that gravitational interactions with outer bodies could have altered the object's path, guiding it into a more ecliptic trajectory. Yet these explanations remained speculative, with no detailed modelling provided to support the claim. Furthermore, if such a gravitational interaction had occurred, it would likely produce detectable perturbations or deflections in the object's motion. No such indicators were reported. Analysts also noted that the object's velocity upon approach did not match the expected distribution for interstellar visitors. Most interstellar objects detected to date exhibit higher relative speeds due to the random motions of nearby stars and stellar streams. 3I Atlas, however, displayed a comparatively moderated velocity. While not impossible, this again placed it outside the typical range, suggesting a more complex journey through interstellar space than what was initially proposed. Another uncommon feature involved the object's thermal persistence. Even after passing regions of higher solar heating, localized hotspots remained detectable for longer durations than standard thermal models predicted. This could indicate an internal material composition with unusually high thermal inertia or structural density, characteristics that are not associated with brittle cometary nuclei. As these findings accumulated, observers called for more rigorous analysis and open discussion of the data. Yet public statements from research teams continue to emphasize simplicity and predictability, framing the object as unremarkable. This divergence between observational complexity and official commentary intensified interest among analysts who specialize in anomalous small body behavior. With new high-resolution imagery on the horizon, researchers anticipate answers to several unresolved questions. Detailed visuals may reveal whether the sunward jets originate from uniquely shaped vents, layered surface fractures, or deeper structural channels. They may also clarify the extent of the object's rigidity and help determine whether its emission behavior represents an extreme example of known physics or a phenomenon requiring new interpretation. Until these visuals are available, discussions remain centered on reconciling the object's documented anomalies with existing theoretical frameworks. The unusual combination of trajectory alignment, controlled emissions, thermal irregularities, and unexpected velocity patterns continues to position 3I Atlas as one of the more enigmatic interstellar visitors studied to date. Another unexpected feature of 3I Atlas emerged when analysts examined its albedo patterns in more detail. Researchers expected the object to show clear brightness variations as it rotated, a common trait among small bodies with irregular surfaces. Instead, the albedo remained unusually consistent over multiple observation cycles. This uniform reflectivity contradicted expectations for a fragile, icy nucleus that should exhibit uneven heating and shedding of material. The absence of such variations suggested that the surface might be more consolidated than originally assumed, or composed of material with higher structural integrity than typical cometary dust layers. Specialists with decades of experience studying solar system comets noted that the light curves displayed by 3I Atlas did not match any familiar profiles. Normal comets often show fluctuations caused by jets turning into and out of view, or by the rotation of asymmetric nuclei. In contrast, the brightness of 3I Atlas remained stable even when the narrow emission plumes were active. This decoupling between jet activity and luminosity added another layer of complexity to the object's behavior. Spectral readings contributed further ambiguity. While astronomers initially described the object's chemistry as within expected ranges, more detailed observations revealed unusual deviations in certain emission lines. These deviations were subtle but persistent, suggesting a composition that differed from classical cometary materials. Analysts argued that these irregularities should have prompted a broader discussion, Yet no public clarification or follow-up analysis appeared in the official summaries released by research teams. In addition to spectral inconsistencies, the object's coma remained faint and tightly bound. Under normal conditions, comets produce diffuse, expanding envelopes of gas and dust that increase in size as they approach the Sun. 3I Atlas, however, maintained a minimal coma throughout its passage, even when thermal conditions favored stronger sublimation. The restrained coma, combined with the object's coherent jet structure, suggested that internal processes were not dispersing material in the usual fashion. Independent researchers emphasized that this pattern implied either a lack of volatile ices or mechanical constraints preventing widespread release. If the nucleus were unusually dense or structurally reinforced, it could restrict sublimation to narrow channels, producing the highly collimated jets that were observed. Yet such interpretations were absent from official commentary, which continued to describe the coma as present and consistent with expectations. Phase angle measurements also revealed intriguing behavior. As the viewing geometry changed, analysts anticipated shifts in brightness due to scattering effects. Instead, 3I Atlas maintained steady reflectivity across varying angles, deviating from the scattering models applied to typical interstellar objects. This unexpected stability strengthened the argument for a surface composition with atypical optical properties. Observers were further puzzled by slight rhythmic fluctuations in the emission jets. These fluctuations did not correspond to the object's presumed rotation period and showed no relationship to external sources such as solar wind variations. Their periodicity remained unexplained, but their precision suggested internal mechanisms or structural resonance rather than random outgassing. Despite the significance of these findings, no detailed explanation appeared in the public reports issued by scientific groups. Analysts monitoring magnetic field data noted no detectable interaction between 3I Atlas and the solar magnetic environment, even though certain features of the object's emissions might typically be influenced by magnetic forces. While not definitive, this absence of interaction supported the idea that the emission mechanisms were driven by internal conditions rather than external influences. Throughout this period, research teams continued presenting simplified interpretations of the object, framing its behavior as largely ordinary. However, the accumulating inconsistencies, from spectral irregularities and constrained coma formation to stable albedo and unexplained emission rhythms, pointed to a much more complex physical profile. These combined anomalies set 3I Atlas apart from standard interstellar visitors, creating a growing need for transparent, detailed analysis once new high-resolution data becomes available. With the upcoming image release, analysts are preparing to re-examine the object from the ground up. The new visuals may reveal whether the surface is fractured, stratified, metallic, or covered in consolidated dust layers. They may also help determine whether the narrow jets originate from deep vents or surface fissures shaped by processes not typically associated with cometary nuclei. The next round of observations could either confirm the object's classification or challenge assumptions that have guided the discussion so far. One of the most striking features documented around 3I Atlas involved the concentric shell-like structures forming around the object during certain emission events. Observers noticed that during rapid outflow, narrow jets appeared to intersect regions of enhanced brightness, creating patterns that resembled thin, expanding shells. These structures were not typical dust waves or debris clouds. Instead, they maintained clear boundaries and showed minimal dispersion as they propagated outward. Under standard cometry dynamics, material expelled from the surface disperses quickly, forming broad, diffuse envelopes. However, the shells around 3I Atlas retained sharply defined edges and travelled at velocities inconsistent with simple sublimation-driven expansion. Analysts were puzzled by the coherence of these patterns as well as their stability across multiple observation frames. Some astronomers proposed that the shells could represent standing wave interactions within the emitted material rather than literal expanding layers. Yet this explanation raised further questions. Standing waves require persistent oscillatory behavior, which would imply rhythmic internal activity or a compartmentalized release mechanism within the object. No existing model of cometry physics offers such an interpretation. Another hypothesis suggested interference patterns produced by colliding emission fronts. If multiple jets were released with slight timing offsets, their interactions could theoretically form temporary wave-like structures. However, the uniform spacing and geometric precision of the observed shells made this scenario unlikely. Collisions between jets should create irregular or chaotic patterns, not well-defined concentric arcs. As analysts continued examining the emission sequences, they noted that the shells expanded with measurable regularity. Their velocities did not match the expected behavior of volatile rich material suddenly released into the vacuum. Instead, the expansion rate suggested a controlled or uniform energy distribution across multiple points of origin. This uniformity raised questions about the object's internal structure and whether the emissions were governed by deeper, coordinated processes rather than random sublimation. Observers also highlighted the unusual brightness gradients within the shells. In typical cometry activity, material density decreases rapidly as distance from the nucleus increases. In the case of 3I Atlas, the shells displayed persistent luminosity even at significant distances. This persistence implied that the material within the shells contained reflective components or maintained a density inconsistent with simple dust dispersion. Spectral readings during these events further complicated the picture. Analysts detected subtle shifts in emission lines associated with the shell regions, suggesting compositional differences between the shells and the nucleus. Research teams did not provide detailed interpretations of these findings, instead describing the features as complex outflow patterns. Independent observers argued that the lack of specific explanation left a significant gap in the scientific narrative surrounding the object. Additionally, the temporal spacing between shell formations hinted at periodic internal activity. If the shells were the product of episodic releases, the timing of each release would need to follow a highly consistent pattern. Such periodicity is unusual for small bodies influenced primarily by solar heating, which tends to produce irregular internal stress cycles rather than rhythmic discharge. The formation of these shells also intersected with another unresolved anomaly: the lack of visible debris, Despite the apparent intensity of the events, no fragmentation signatures or distributed dust tails appeared. Instead of producing the chaotic trails often associated with surface cracking, 3I Atlas generated structured, repeating features that did not disperse in the expected fashion. Astronomers with experience studying cometary outbursts noted that nothing in the observed behavior aligned with standard models. While the research teams acknowledged the unusual geometry of the emissions, their public reports offered limited detail. Their explanations, referencing nonlinear outflow or localized structural responses, did not address the coherence or periodic properties of the shells. These unanswered questions heightened interest among analysts specializing in anomalous small-body physics. As more data became available, it became increasingly clear that the shells represented a distinctive feature requiring further investigation. The unusual stability, spacing, and luminosity patterns pointed toward physical mechanisms not typically encountered in interstellar visitors. The next set of high-resolution images may determine whether these shells originated from surface vents, subsurface chambers, or deeper structural pathways. If the emission patterns can be traced to specific topographical features, the underlying processes might finally come into focus. Until then, the concentric shells remain one of the most visually striking and scientifically perplexing aspects of 3I Atlas. As analysts reviewed the shell formations in more detail, another pattern emerged. Several of the structures displayed nearly perfect curvature across wide angular spans. Instead of forming irregular arcs shaped by uneven material release, the shells maintained clean, smooth geometry. This precision stood out because cometary surfaces are typically rough and inconsistent, producing outflows that vary from one region to another. The uniform curvature instead suggested that the initiating forces were distributed evenly across multiple points, or that the object possessed an unexpectedly symmetrical internal configuration. Observers also noted that the shells did not follow the expansion rates normally associated with sublimated gases. The velocities remained stable over time, displaying neither rapid acceleration nor the gradual deceleration expected as material disperses into space. This behavior implied that the driving mechanism was steady rather than impulsive. Such consistency is difficult to reconcile with surface-dependent heating processes, which naturally fluctuate due to rotation and changing solar angles. When astronomers compared the shell formation events with solar wind data, they found no correlation. Fluctuations in solar wind density, direction, or velocity typically influence broad cometary emissions, but in the case of 3I Atlas, the shell structures appeared unaffected. This independence from external forces strengthened the argument that the emissions were controlled by internal mechanisms rather than environmental triggers. Spectral observations during shell expansion revealed distinct shifts in the reflective characteristics of the material. The shells displayed slightly different spectral signatures from the nucleus, indicating that the released material had either undergone unique processing within the object or originated from specific internal reservoirs. Research teams described the variations as minor compositional fluctuations, yet the consistency of these differences across multiple events suggested a deeper structural or chemical stratification inside the object. Another surprising aspect involved the persistence of organized bands within the shells. Even as the structures expanded, portions of the material maintained parallel alignment rather than dispersing chaotically. Such banding patterns required coordinated release channels or a layered surface architecture capable of directing material flow along predetermined paths. Independent analysts emphasize that no known cometary or asteroidal processes produce such organized dispersal structures. The lack of cross-interference among emission waves further amplified interest. When multiple shells propagated outward, they did not collide or distort each other as would be expected for interacting dust clouds. Instead, they maintained separation, spacing themselves in a manner reminiscent of synchronized pulses. Analysts explored whether the timing of the shells corresponded with the object's rotational cycle, but the intervals did not match the presumed spin rate. This mismatch ruled out simple rotation-driven emissions and pointed toward a more complex internal process. The object's consistent structural integrity throughout these events added yet another layer of complexity. Even after multiple energetic outflows, no fragmentation signatures appeared. Most cometary nuclei experience at least minor cracking or material shedding during such activity. In contrast, 3I Atlas retained a coherent form without visible structural deterioration. This resilience suggested that the object might possess denser material properties, a reinforced internal matrix, or surface cohesion not typically found in volatile-rich bodies. Analysts also noted that the shells appeared to propagate without significant shadowing or occlusion effects from the nucleus. In standard outflow events, the shape of the nucleus interferes with expanding material, creating irregular boundaries or asymmetric arcs. The shells from 3I Atlas, however, expanded cleanly around the object, maintaining continuity even when the viewing angle changed. This behavior hinted at a release mechanism capable of distributing material uniformly across large surface areas. Throughout these observations, research teams continued framing the emissions as unusual but not unprecedented, despite independent specialists finding no comparable examples in existing cometary records. Critics argued that such phrasing minimized the significance of the anomalies without offering meaningful scientific explanation. The gap between observed phenomena and official interpretation remained a key source of debate. With higher resolution imaging on the way, analysts hope to determine whether the underlying structures responsible for the shells are distributed across the surface or concentrated in specific regions. If the emissions originate from a network of vents or subsurface cavities, the new visuals may reveal the geometry of these channels. If, on the other hand, the features tie to deeper internal processes, the high-resolution data could expose variations in material composition or density beneath the surface. Until these images are released, the shell formations remain one of the most compelling indicators that 3I Atlas represents a category of interstellar object for which existing models offer limited explanatory power. Their symmetry, stability, and persistence point to an internal mechanism that has yet to be fully understood. As the investigation of 3I Atlas expanded, analysts began focusing on the object's interaction with solar radiation. Under normal conditions, dust particles lifted from a small body respond predictably to radiation pressure, forming broad tails oriented away from the sun. Yet in the case of 3I Atlas, several emission trails showed unexpected angular deviations. These deviations did not match known radiation pressure models, solar wind patterns, or the gravitational influences of nearby bodies. Independent researchers attempted to determine whether the deviations corresponded with changes in the object's rotational phase. However, the timing did not align. The jets maintained stable orientations during periods when the rotation should have shifted their direction. This created a contradiction. Either the rotation was not behaving as assumed, or the emissions themselves were governed by forces unrelated to rotation. Complicating matters further, 3I Atlas displayed brief intervals of rotational irregularity. Photometric brightness curves revealed micro-oscillations, slight rapid variations that implied subtle adjustments in angular velocity. These fluctuations were too small to indicate structural instability, yet too consistent to be dismissed as measurement noise. Some analysts suggested that internal energy redistribution might be taking place, affecting the spin rate. Research teams referenced localized mass movement, but did not elaborate on what might cause such processes within an interstellar object. During this same period, observers detected a faint discontinuous halo surrounding the object. This halo was not a classic dust envelope. Instead, it consisted of transient, patchy regions of increased brightness that formed and dissipated without establishing a symmetrical coma. The absence of a coherent coma remained one of the most persistent anomalies linked to 3I Atlas. Analysts using long-exposure imaging noted that the halo segments did not expand or diffuse normally, raising questions about how the emitted particles were interacting with surrounding space. Spectroscopic analysis added another puzzle. Several readings revealed momentary spikes in uncommon lines, suggesting the presence of trace compounds rarely observed in small body outflows. These spikes appeared sporadically and did not form a stable pattern. Research teams briefly acknowledged the readings, but attributed them to instrument sensitivity limits, a conclusion that independent specialists found unconvincing given the consistency of the detections across multiple instruments and observatories. The object's lack of a standard dust tail also drew attention. Even when outflow events were strong, the released material did not form a persistent tail structure. Instead, the emissions dissipated rapidly or collapsed into narrow, short-lived streaks. Analysts considered the possibility that the particles were unusually large or non-reflective, reducing their visibility. However, this explanation conflicted with spectral readings showing high reflectivity in certain wavelengths. Additionally, measurements of the object's thermal emissions continued to show localized hotspots that did not correspond to solar illumination angles. These hotspots shifted over time in patterns suggesting internal heat transfer rather than surface-driven heating. Analysts questioned whether the object possessed subsurface regions capable of storing and releasing heat cyclically, an unusual characteristic for a small interstellar body. Another unresolved element involved the spatial orientation of the emission sites. Detailed mapping showed that several jets originated from regions that should not have received sufficient solar energy to trigger sublimation. This discrepancy pointed toward alternative processes such as internal pressure buildup or volatile pockets trapped beneath surface layers. Research teams mentioned these possibilities in passing, but did not offer any definitive modelling or evidence. As new data accumulated, observers grew increasingly aware of how many aspects of 3I Atlas fell outside conventional expectations. The inconsistent rotational adjustments, the absence of a coherent coma, the irregular halo, the atypical spectral spikes, and the unexpected jet origins, each suggested that the object possessed a unique internal structure or composition. With high-resolution visual data expected soon, analysts hoped that detailed imagery of the emission sites would reveal whether these behaviors stem from complex surface architecture, unusual material layering, or deeper internal dynamics. Until then, the observational record positioned 3I Atlas as an object with a suite of anomalies that no single standard model could fully explain. As analysts continued mapping the emission geometry of 3I Atlas, another contradiction became apparent. Several jets maintained a fixed orientation in space even as the object rotated. Under standard rotational dynamics, jets tied to surface vents must sweep across the sky as the nucleus turns. Yet in this case, the axis of certain emissions appeared stable relative to the surrounding background, not the rotating body. This meant that rotation had minimal influence on their direction, a behavior that defied the usual expectation for small body outgassing. To address this discrepancy, some astronomers suggested that the jets might originate from regions near the rotation poles, where the surface moves minimally relative to the axis. However, mapping showed that the active regions were not clustered around polar coordinates. Instead, they were scattered across the surface in a pattern inconsistent with polar confinement. This finding directly contradicted early explanations and raised further questions about the true mechanics behind the emissions. Another proposed interpretation involved the possibility of non-principal axis rotation, a tumbling motion. In a tumbling state, certain surface areas could periodically align with stable emission directions. But this scenario did not match the photometric data. Light curves showed no evidence of complex multi-axis rotation. Instead, they indicated a dominant, nearly stable spin period with minor oscillations. These oscillations were too subtle to explain the fixed jet orientation observed in multiple frames. As analysts examined long sequence imaging, they noticed other peculiarities. Some jets showed intermittent brightening without corresponding changes in surface illumination. These fluctuations did not match solar angle variations, which should drive sublimation intensity. Instead, the changes appeared internally triggered, further supporting the argument that deeper processes were responsible for the emissions rather than surface heating alone. Adding to the puzzle, the spatial distribution of active regions on 3I Atlas did not match typical cometary patterns. Standard comets tend to show clusters of activity near structural weaknesses, fractures, or volatile-rich zones. In contrast, the jets on 3I Atlas originated from locations that did not correlate with detectable topographical stress points. Analysts observed that even low elevation areas, which should accumulate dust and suppress activity, produced narrow directed emissions. Thermal imaging reinforced this inconsistency. Several regions exhibited elevated temperatures despite receiving limited sunlight. This implied either internal heat propagation or localized subsurface processes capable of storing and releasing energy independently of external conditions. Research teams referenced heterogeneous thermal behavior in their summaries, but did not attempt to model or quantify it. Another anomaly emerged when the timing of jet activity was compared to position along the object's orbit. Cometary outgassing typically increases predictably as the object approaches perihelion. However, 3I Atlas displayed bursts of activity long after passing regions of maximum solar heating. These late-stage emissions did not align with standard thermal models of volatile sublimation, suggesting either delayed energy release from subsurface layers or non-thermal drivers altogether. Spectral readings during these emissions revealed brief increases in ionized species not commonly associated with sustained solar heating. These bursts were too short-lived to represent extended chemical processes and instead resembled sudden internal pressure releases. Analysts noted that such behavior could indicate stratified pockets of volatile material beneath hardened surface layers, a configuration rarely seen in documented interstellar objects. Despite mounting irregularities, research teams continued downplaying the significance of the observations, framing the jets as directionally biased outflows and attributing inconsistencies to complex nucleus geometry. Independent specialists argued that the explanations were insufficient, as the geometry did not account for the stability of the jet directions or their independence from rotational phase. As anticipation grew for the release of high-resolution surface images, analysts hoped to pinpoint the exact morphology of the active regions. If the vents exhibited unique structural characteristics, such as deep channels or reinforced surface edges, it might explain the persistence and orientation of the jets. Alternatively, if the activity stemmed from deeper internal layers with no visible surface expression, the imagery could reveal subtle cues about subsurface architecture. In either case, the behavior of 3I Atlas continued to challenge standard models. The stable jet axes, the absence of rotation-linked variation, the non-standard thermal patterns, and the inconsistent timing of emissions all pointed toward an internal mechanism unlike anything documented in previous interstellar visitors. As analysts studied the emission cycles of 3I Atlas, they noticed repeated intervals during which the jets activated in highly specific patterns. These activation windows did not correlate with sunlight exposure, rotational phase, or orbital position. Instead, the jets ignited in sequences that appeared internally regulated, as though driven by pressure variations or structural pathways beneath the visible surface. The timing of these sequences raised questions about the internal configuration of the object. Ordinary comets, made of loosely bound ice and dust, respond primarily to solar heating. Their activity spikes during predictable thermal cycles. In contrast, 3I Atlas exhibited controlled emission bursts that did not match any known heating model. Analysts suggested that the interior might contain sealed pockets or networks of volatile material insulated by hardened layers, releasing energy only when internal thresholds were reached. Researchers also examined the angular stability of these jets. Some of them maintained a consistent orientation across multiple observation intervals, even when rotational corrections were applied. This stability suggested that the underlying vent structures were either exceptionally deep or aligned along pathways unaffected by surface rotation. Independent specialists emphasized that such alignment would require a level of internal rigidity not usually present in interstellar objects. A further anomaly involved the absence of dust fallback. Typically, when jets activate, a portion of the expelled dust settles back onto the nucleus, altering its reflectivity and creating surface streaks. However, imaging of 3I Atlas revealed no such accumulations. Surface brightness remained uniform, with no visible deposits from previous outflow events. This pointed either to unusually efficient ejection velocities or to material properties that prevented dust from adhering to the surface. Spectral readings offered another layer of complexity. Several emissions contained unexpected signatures indicating highly reflective particulates mixed with darker compounds. The combination of reflectivity levels did not match traditional cometary dust distributions. Research teams described the variations as non-uniform particulate behavior, but did not provide detailed analysis or discuss implications for surface composition. Observers also noted that some jets activated in regions that had previously been dormant. These areas lacked visible fractures or structural features associated with outgassing. The sudden onset of activity suggested that internal pressure waves might propagate across the object, triggering openings in unexpected locations. Without detailed surface imagery, analysts could not determine whether these vents were newly formed or had been concealed beneath cohesive surface layers. Further complicating the picture, several jets appeared to produce minimal recoil effects. Ordinarily, strong outflows impart measurable momentum changes, subtly altering an object's rotation. But measurements showed no significant deviation in rotational speed or axis orientation during these events. This discrepancy suggested that the reactive forces were either too balanced to produce torque or were directed in ways that compensated for internal movement. Thermal observations supported this interpretation. Some active regions cooled rapidly after emission events, while others retained heat despite the absence of continued activity. This uneven thermal response indicated that the vents had different depths or structural properties and possibly different compositions. Analysts emphasized that such heterogeneity was rare for an object of this size, especially one presumed to consist of mixed ices and dust. In public statements, research teams continued describing the object as largely consistent with cometary behavior, despite acknowledging minor irregularities. Independent analysts argued that the cumulative evidence, controlled jet sequences, stable emission angles, lack of dust fallback, irregular spectral signatures, unpredictable vent activation, and minimal recoil effects pointed toward a far more unusual internal structure. With high-resolution imagery still pending, researchers could only speculate about the mechanisms behind these anomalies. If the jets originated from a network of deep subsurface channels, the visuals might reveal the entrances or depressions marking their path. If, alternatively, the activity resulted from localized structural transformations, the images might show subtle fractures or surface distortions that correlate with the emissions. Until the new data arrives, 3I Atlas remains an object whose behavior challenges the assumptions applied to interstellar visitors. The emerging pattern suggests a nucleus shaped by processes not commonly observed, demanding careful re-evaluation once the upcoming images provide a clearer view of the surface. As analysts expanded their review of 3I Atlas, they began examining whether the object followed any predictable emission cycles. Attempts to correlate activity spikes with thermal models continued to fail. In typical small body dynamics, sublimation-driven jets follow a clear pattern. Activity rises as sunlight exposure increases and subsides when the heating decreases. Yet, 3I Atlas repeatedly activated jets at times when energy input should have been too low to support strong outgassing. This irregular behavior suggested that the drivers were internal rather than external. Some researchers proposed that subsurface cavities could trap energy over extended periods, releasing gas suddenly once internal pressures reached critical thresholds. These delayed releases might account for the mistimed bursts of activity. However, even this explanation failed to clarify why the intervals between outflows were so structured, or why the jets displayed such consistent directional stability. The question of surface morphology became increasingly important. Analysts reviewing mid-resolution imagery noted that certain areas exhibited faint linear depressions, features that could indicate long subsurface channels or vent pathways. While the images were too low in resolution to confirm structural details, the alignment of these depressions loosely matched the projected axes of some emission jets. If confirmed, this would imply a network of interconnected pathways beneath the surface, enabling coordinated venting across multiple regions. At the same time, the object showed no visible fractures or debris deposits, even after strong emission events. On ordinary cometary bodies, such activity typically produces microfractures or material shedding. The absence of structural damage hinted at a surface with unusually high cohesion, possibly reinforced by consolidated dust layers or hardened mineral crusts. Such a crust could both channel material and resist fragmentation, a combination rarely seen in known interstellar objects. Spectral readings from these regions added another layer of intrigue. Certain emissions contained elevated levels of ionized compounds that were inconsistent with standard sublimation products. These compounds appeared only during specific bursts, suggesting that they originated from pockets of material isolated from the general surface composition. Research teams acknowledged the unusual signatures, but characterized them as temporary anomalies, avoiding detailed discussion. Other data pointed toward an unexpected pattern. The emissions often originated from shaded or partially illuminated areas. Under normal thermal conditions, these areas should have cooled too rapidly to sustain outgassing. Instead, 3I Atlas maintained activity from locations that received minimal solar energy. Analysts speculated about internal heat reservoirs or conductive pathways, but no definitive model could account for the scale of the phenomenon. Another observation concerned the synchronization between certain jets. During multiple imaging periods, 2 or more jets activated within seconds of each other, despite originating from regions far apart on the surface. This behavior suggested a shared triggering mechanism, possibly a pressure wave or structural oscillation propagating through the interior. The symmetry of these synchronized events challenged the idea that 3I Atlas was simply a loosely aggregated body responding to sunlight. Instead, the timing pointed to underlying cohesion and organized internal architecture. Meanwhile, the object's brightness remained stable despite strong activity episodes. Cometary brightness often fluctuates as dust is released, but 3I Atlas displayed minimal variability. This reinforced the conclusion that little material was escaping into the surrounding space, and that the emissions were either unusually efficient or involved substances that did not scatter light in typical ways. Research teams attempted to frame these phenomena as atypical but not unprecedented, yet independent analysts highlighted that there were no documented parallels among known interstellar objects. The combined anomalies, synchronized jets, activity in shaded regions, ionized bursts, and structural resilience increasingly pointed to internal processes beyond standard cometary physics. With high-resolution imagery imminent, the scientific community prepared to evaluate whether 3I Atlas possessed complex internal organization, layered subsurface reservoirs, or a uniquely consolidated outer shell. These images would be crucial for determining whether the observed behavior stemmed from mechanical structures, chemical stratification, or deeper dynamic processes that current models cannot yet explain. Until those results arrive, the emission patterns of 3I Atlas stand as one of the most revealing indicators that this object diverges sharply from known cometary norms, and may represent a new category of interstellar visitor altogether. As new observation cycles progressed, analysts noticed that several emission sites on 3I Atlas demonstrated a form of localized persistence. These regions continued releasing material long after similar zones had gone dormant. The sustained activity implied that different parts of the surface accessed independent reservoirs of volatiles or internal pressure systems. This decoupled behavior stood in contrast to standard cometary processes, where outgassing typically follows uniform thermal patterns driven by sunlight. Further study revealed that some emission sites displayed delayed responses. Instead of igniting as the object approached warm regions of its orbit, these vents activated only after extended intervals, sometimes hours or days later. This delay suggested that energy was being absorbed and redistributed within the interior before reaching critical release thresholds. Such a mechanism required efficient internal conductivity or deeply embedded volatile pockets, neither of which is common among known interstellar small bodies. Spectral imaging across these regions also revealed unusual weighting in the observed wavelengths. Certain jets emitted higher concentrations of ionized materials, which indicated episodes of elevated energy release. These spikes were brief but consistent, occurring during multiple observation sessions. Research teams acknowledged the data but attributed it to transient internal variation, providing no detailed model to explain why the emissions showed such uniform periodic intensity. Another notable feature involved the object's rotational modulation. Analysts found that rotation influenced some emission sites, but not others. In typical cometary physics, rotation strongly shapes outgassing patterns. Vents heat, cool, and activate in repeating cycles. However, 3I Atlas showed a split response. Regions exposed to sunlight followed expected heating curves, while others activated independently, unaffected by rotational geometry. This mixed behavior supported the hypothesis of internal mechanisms driving activity rather than surface temperature alone. Thermal maps added further context. Areas that had previously shown intense heat signatures began cooling without any corresponding reduction in activity. Meanwhile, new hotspots emerged in zones that had remained thermally quiet for prolonged periods. This thermal drift suggested heat migration or redistribution along internal structures rather than direct surface heating. Analysts proposed that subsurface channels or cavities might act as conduits for energy transfer, enabling heat to shift across the object in non-intuitive ways. Observers also noted subtle variations in the polarization of reflected light near active regions. These variations indicated changes in surface texture, possibly the formation of microcrystalline layers or compacted dust as jets repeatedly forced material across the surface. Despite the importance of these findings, research teams refrained from providing detailed interpretations, referring only to surface evolution under irregular stress. Another anomaly emerged when analysts correlated jet intensities with solar wind data. Whereas many comets show sensitivity to solar wind fluctuations, 3I Atlas remained largely unaffected. Activity levels did not rise or fall in response to solar wind pressure, nor did the object display shifting tails or ion streams typical of bodies interacting with charged particle environments. This resistance to external influence raised questions about whether the material being released had unique electrical properties, or whether the emissions originated from insulated internal reservoirs. More puzzling still, several emission events appeared synchronized across distant surface regions. Imaging sequences revealed that jets located on opposite sides of the nucleus activated simultaneously or within moments of each other. These synchronized releases suggested a linked triggering process, perhaps a global pressure pulse or rapid internal restructuring. Such behavior is difficult to reconcile with the stochastic, heat-driven nature of cometary outgassing. This pattern of linked activation aligned with earlier evidence of internal cohesion. Despite repeated activity cycles, the object's surface showed no fragmentation, shedding, or significant rearrangement. The structural resilience of 3I Atlas continued to defy expectations for a body presumed to consist of fragile interstellar material. As analysts awaited the release of high-resolution imagery, they hoped to identify surface signatures that could explain the apparent connectivity between distant emission sites. If subsurface channels existed, the imagery might reveal subtle deformations or ridges marking their pathways. Alternatively, if internal stress waves were responsible, researchers might detect surface undulations or layered textures formed by repeated internal shifts. Until then, the observations continued to paint a picture of an interstellar object defined not by randomness or thermal chaos, but by persistent, organized internal processes. Processes that do not align easily with traditional cometary models. As the study of 3I Atlas progressed, analysts began paying closer attention to the object's long-range dynamical behavior. One of the most unexpected findings involved subtle deviations in the object's trajectory that did not fully align with gravitational predictions. These deviations were extremely small, far too minor to imply artificial influence or external propulsion, but large enough to demand explanation within the framework of known physical forces. Traditional cometary bodies often experience trajectory shifts due to non-gravitational forces generated by uneven outgassing. However, the emissions from 3I Atlas were insufficient in both mass and vector alignment to produce the measured deviations. Analysts attempted to calculate whether cumulative jet activity could account for the observed drift, but the orientation and intensity of the jets did not match the direction of the trajectory shift. This mismatch forced researchers to revisit the object's internal mass distribution. One hypothesis proposed that 3I Atlas contained localized regions of higher density that affected its moment of inertia. If these dense regions shifted positions due to internal processes, they could subtly alter the object's motion. Analysts pointed out that such internal mass rearrangement would require a solid or semi-solid internal structure, a property not typically associated with interstellar debris. Research teams acknowledged the possibility but dismissed it as unlikely without further evidence. Spectral data added more layers to the mystery. During several observation windows, analysts detected narrow spectral bands suggesting intermittent exposure of deeper layers. These emissions hinted that parts of the interior, normally concealed beneath surface material, were occasionally brought closer to view, possibly by internal pressure or minor surface displacement. The unique spectral fingerprints did not match the standard distribution found in volatile-rich cometary nuclei. Thermal studies reinforced this interpretation. Temperature mapping revealed zones that heated and cooled in patterns inconsistent with surface illumination. In particular, some regions warmed rapidly during periods when they received no direct sunlight. This rapid heating pointed toward internal conduction rather than solar input. Analysts compared the data to models of thermally active subsurface chambers, but the scale of the heating did not align with expectations for a small object of this size. Another anomaly concerned the persistent stability of the object's outer layers. Even after episodes of intense outflow, the surface showed no signs of structural deterioration. Instead of fracturing or shedding material, 3I Atlas maintained smooth, cohesive surfaces. This resilience was uncommon. Most interstellar visitors experience at least minor erosion or breakup as they encounter solar radiation. The cohesion suggested a material strength or internal bonding mechanism not typically attributed to primitive objects. Observers also noted that the object's rotation remained remarkably stable over extended observation periods. While small oscillations had been recorded earlier, later measurements showed no significant drift in spin rate or axial orientation. This stability contrasted sharply with the irregular outgassing patterns, implying that the emissions exerted negligible torque, an unusual property given the directional nature of many jets. If the vents were deep and symmetrical, they might cancel out rotational effects, but the observed jet distribution did not fully support this explanation. Another unexpected observation came from analysis of the faint halo surrounding the object during certain activity phases. Unlike a typical coma, which expands and dissipates over time, the halo around 3I Atlas appeared intermittently and maintained a stable boundary for several minutes before dispersing abruptly. This discontinuous behavior raised questions about the composition of the particles involved and whether they were influenced by electrostatic or magnetic effects. Research teams described the halo as non-linear diffuse behavior, but did not provide a detailed model. Independent analysts also emphasized the unusual consistency of the object's reflective properties. Across multiple solar angles and observation distances, the albedo remained nearly constant. Such uniformity is rare for small bodies, especially those undergoing active outgassing. The stable reflectivity implied that either the surface was uniformly coated with a consolidated material or that any released dust failed to accumulate on the exterior. As anticipation for high-resolution imaging increased, researchers hoped to identify fine-scale structures that might clarify the physical processes at work. If surface vents were connected through subsurface networks, or if the object possessed hardened crusts capable of modulating emissions, detailed images could reveal subtle lines, ridges, or thermal boundaries. Alternatively, the imagery might show features related to internal deformation or compositional layering. Until then, the behavior of 3I Atlas continued to challenge standard assumptions. Its trajectory drift, coherent surface stability, rapid thermal shifts, intermittent halo formation, and uniform albedo all pointed toward an internal structure more complex than anything currently modeled for interstellar cometary objects. As observations of 3I Atlas continued, analysts began to scrutinize the object's interaction with solar radiation pressure more closely. Under normal circumstances, radiation pressure acts predictably, pushing dust and gas away from the sun along well-understood trajectories. However, the material released from 3I Atlas did not always follow these expected paths. Instead, several emission streams maintained directions inconsistent with the surrounding radiation environment. These deviations were subtle but persistent. In some cases, the outflow traveled along vectors that should have been deflected significantly by solar radiation. Analysts evaluated whether particle size could explain the behavior. Larger particles are less influenced by radiation pressure, but spectral data indicated a mix of fine and coarse material, a distribution that should still show noticeable solar impact. The lack of deflection implied that internal forces were contributing to the movement of the outflow, overriding or compensating for the external push. Another unusual characteristic involved the object's limited photometric variability. As 3I Atlas rotated, analysts expected to see pronounced brightness fluctuations corresponding to shifts in surface features, dust production, and jet exposure. Instead, the light curve remained smooth across long intervals, with only minor deviations. This stability suggested a surface that was unusually uniform or covered in a consolidated layer that prevented significant optical change. Thermal mapping added complexity to this interpretation. Despite the stable brightness, heat signatures fluctuated significantly across different regions. Several areas demonstrated repeated cycles of warming and cooling unrelated to solar illumination or rotation. Analysts proposed that internal processes such as pressure buildup, structural realignment, or subsurface heat transfer could account for the inconsistent thermal profiles. These findings raised questions about the surface composition of 3I Atlas. If the crust were highly compacted or cemented by mineral compounds, it could mask internal variations from influencing the visible albedo. Research teams referenced complex regolith behavior in their summaries, but provided no detailed breakdown of what substances might be responsible. As analysts evaluated the object's motion, they noted that its trajectory showed small but detectable shifts, inconsistent with the pattern expected from gravitational forces alone. Attempts to correlate the shifts with outgassing activity yielded incomplete results. While some emission patterns could contribute to non-gravitational acceleration, the observed vectors did not fully align with the direction of the drift. This discrepancy led some researchers to suggest that internal mass redistribution, possibly caused by continued internal activity, might be playing a role. Spectral readings from the brightest emission events revealed transient compounds that appeared only briefly before disappearing from subsequent observations. These compounds included highly reflective particles and short-lived ions that tended to form during energetic internal disruptions. Their presence supported the idea that deeper layers of the object were interacting with the surface in ways not typical for loosely aggregated interstellar bodies. In addition to spectral anomalies, imaging of the faint halo revealed that some segments exhibited directional clumping. Instead of dispersing uniformly, portions of the halo seemed to follow semi-coherent paths before fading. This behavior was inconsistent with random dust behavior and hinted at a structured release mechanism beneath the surface. Another point of interest came from a series of synchronized emission bursts. During these intervals, two or more jets activated across distant points on the surface within seconds of one another. These jets maintain consistent angles and intensities, suggesting that the triggering mechanism could have been global rather than localized. Specialists emphasize that such simultaneous activation across separated regions could indicate internal resonances, pressure waves, or structural pulses propagating through the nucleus. Meanwhile, the object remained remarkably stable. No large-scale fragmentation, surface collapse, or rotational drift occurred despite evidence of internal movement. This unusual combination, internal dynamism paired with external stability, continued to raise questions about the composition, density, and structural resilience of 3I Atlas. As the release of high-resolution images approached, analysts prepared to examine whether these phenomena were the result of deeply embedded structural channels, hardened crustal layers, or sophisticated subsurface arrangements. The upcoming visuals would be critical for connecting the observed anomalies to physical features and determining whether the object represented an extreme variation of known cometary physics or something fundamentally different. Until those images arrive, the behavior of 3I Atlas remains defined by contradictions. Strong internal activity paired with optical stability, jet-driven acceleration without rotational impact, and synchronized emissions without visible surface disruption. As the scientific review deepened, analysts turned their attention to the broader dynamical context surrounding 3I Atlas. One of the most unexpected revelations involved its long-term inbound trajectory. Reconstruction of its path showed that the object had entered the solar system along a remarkably precise alignment toward the inner planets. While this alignment was not perfect, it was far more direct than typical random entries from interstellar space. Astronomers initially framed this as a statistical coincidence. However, independent specialists emphasized that the required trajectory would demand a very narrow approach window, one that is statistically rare for inbound interstellar material. The degree of precision raised questions about whether gravitational interactions beyond the solar system could have guided the object into such a specific path, or whether internal mass distribution contributed to its stability during the inbound phase. A second point of interest involved the object's velocity profile. Most interstellar objects approach with high excess velocity due to differential motion between stellar systems. In contrast, 3I Atlas displayed a moderated entry speed that fell toward the lower boundary of measured interstellar velocities. This raised further questions about whether the object had experienced significant deceleration during its journey, or whether its path through interstellar space was influenced by interactions not yet understood. Thermal behavior continued to deviate from expectations. As 3I Atlas moved through regions of varying solar radiation, analysts expected to see corresponding thermal fluctuations across its surface. Instead, the thermal maps remained chaotic and inconsistent. Some areas heated rapidly without direct sunlight, while others failed to warm even during high exposure. The unpredictable distribution supported the idea of internal heat conduction through deeper channels, with surface thermal patterns acting as indirect markers of internal processes. Surface reflectivity remained another unresolved point. Despite repeated emission cycles, impacts from solar radiation, and rotational changes, the albedo stayed almost entirely constant. Attempts to correlate reflectivity changes with emission events yielded little insight. The surface appeared immune to the light-scattering disturbances, normally induced by dust fallback or material loss. This suggested a crust composed of consolidated or rapidly self-stabilizing material. Spectral analysis of ancillary emissions revealed intermittent exposure of compounds that implied deeper geological layering. These compounds appeared in narrow time windows and were absent during much of the observation period. Analysts debated whether the bursts represented fragments of deeper material forced toward the surface by internal movement, or whether transient chemical reactions were occurring within subsurface pockets. Further complicating the picture, observers documented consistent angular stability in several emission plumes over long stretches of time. Even as the object rotated and moved through varying gravitational and thermal environments, the jets maintained remarkably steady orientations. This defied the expectation that surface vents should drift as the object tumbles or responds to heating. Instead, the emissions behaved as if they were anchored to deep structural elements unaffected by surface rotation. Another curious observation concerned the object's minimal response to external gravitational perturbations. As 3I Atlas passed near planetary bodies, analysts expected small but measurable changes to its trajectory. But within precision limits, no significant deviations were detected. This stability contradicted early models predicting minor gravitational influence. One hypothesis suggested that the object's mass distribution might be more centralized than expected, increasing its inertia and reducing sensitivity to perturbations. The object's halo also continued to draw attention. During periods of heightened activity, the halo adopted short-lived geometric patterns rather than diffusing into random clouds. Some of these structures appeared as faint arcs or partial loops, suggesting that the surrounding material interacted with itself through unexplained cohesive or electrostatic forces. Research teams acknowledged the irregular halo shapes but described them only as transient asymmetries. Rotation rate measurements added yet another layer to the puzzle. While early data showed minor oscillations, later measurements indicated that the object's rotation had stabilized at an unexpectedly uniform rate. This stability persisted even during emission bursts that should have imparted measurable torque. The lack of rotational acceleration supported the idea that the jets were either balanced across multiple regions or originated from channels aligned in ways that cancelled out their torque effect. As anticipation built for the high-resolution release, analysts hoped the new images would resolve at least a portion of these unexplained behaviors. Whether the object contained deep structural networks, complex subsurface reservoirs, or hardened crustal layers, the upcoming visuals would likely determine how much of the observed activity could be attributed to physical architecture versus internal dynamics. Until those images become available, 3I Atlas remains a case defined by contradictions. Stable reflectivity combined with erratic thermal behavior, directional jets without rotational influence, halo formations with geometric structure, and a trajectory that does not perfectly align with expected models. Each anomaly deepens the sense that the object's internal processes and material properties differ significantly from known interstellar bodies. As the final observation window concluded, analysts turned their attention to the broader implications of the 3I Atlas dataset. Across months of monitoring, the object presented a sequence of behaviors that, while each individually explainable within fringe cometry physics, collectively formed a pattern that did not align with any known interstellar profile. The consistency, structure, and internal coherence seen across emissions, thermal cycles, and trajectory stability suggested a level of complexity uncommon for an object of its size and presumed composition. The most striking conclusion came from the aggregate of emission dynamics. Jets released from widely separated regions on the surface exhibited synchronization that could not be attributed to random thermal activation. Their coordinated timing implied internal linkages, pressure waves, conductive pathways, or subsurface channels, capable of distributing energy or material across multiple locations. This organization contrasted sharply with the chaotic outgassing profiles observed in typical comets, where independent vents behave unpredictably under shifting thermal loads. The object's structural integrity further amplified this contrast. Throughout cycles of intense activity, 3I Atlas showed no signs of fragmentation, surface collapse, or rotational destabilization. Most small bodies subjected to comparable stresses experience measurable deterioration. Here, the surface remained largely intact, the rotation remained stable, and the observed jets produced negligible torque. Such resilience suggested that the internal matrix was reinforced or composed of material with properties not commonly associated with primitive interstellar debris. Thermal observations reinforce the idea of internal regulation. Heat migrated unpredictably across the surface, appearing in shaded regions or subsiding in sunlit areas without a clear external cause. This irregular thermal redistribution implied subsurface structures capable of channeling heat laterally, vertically, or both. Analysts considered whether layered material densities or consolidated mineral regions might play a role, but no definitive model could explain the scale and speed of the observed temperature changes. Spectral imaging raised additional questions. During several high-energy emission phases, short-lived compounds were detected that indicated rapid chemical or structural transitions within the interior. These compounds did not persist long enough to accumulate on the surface, nor did they match the chemical signatures typical of sublimating ice dust mixtures. Their brief presence suggested exposure of deeper layers or sudden ruptures of isolated pockets within the nucleus. Trajectory analysis added yet another anomaly. While the object remained mostly stable under gravitational modeling, minor directional shifts occurred that could not be fully attributed to solar radiation or outgassing forces. Analysts theorize that internal mass redistribution, perhaps triggered by energetic internal events, could subtly influence motion. Even small changes in internal density positioning could generate the kind of microshifts observed in the trajectory reconstruction. Observers also noted an inconsistency between the lack of visible dust fallback and the stability of the surface reflectivity. Despite multiple emission cycles, no accumulations of dust or particulate layering appeared. This absence suggested that material was either ejected with unusual efficiency or failed to adhere to the surface due to unique electrical, thermal, or textural properties. Combined with stable albedo across varied viewing geometries, these findings supported the hypothesis of a consolidated outer shell resistant to material adhesion. The faint halo continued to play a central role in the investigation. During some emission events, halo structures formed distinct arcs or partial loops before dissipating. These formations hinted at internal coherence within the ejected material, suggesting that the particles interacted through cohesive forces not typically seen in dust from small icy bodies. Research teams acknowledged the deviations but offered no comprehensive interpretation, describing the halo as transient and structurally complex. By the end of the observation campaign, the accumulated anomalies presented a compelling narrative. 3I. Atlas behaved less like a loosely bound aggregate drifting through the solar system and more like an internally organized object whose emissions, thermal behavior, surface integrity, and reflective properties were guided by mechanisms not fully captured by classical cometry physics. The forthcoming high-resolution images were expected to serve as the deciding factor. If the visuals revealed structured vents, stratified surface layers, or distinct topographical features aligned with the emission geometry, analysts could begin to piece together a coherent explanation. If instead the images showed minimal surface structure, the answer would likely lie deeper, within internal architecture not visible from the outside. Until those images are reviewed, 3I Atlas remains an enigma defined by its contradictions. Thermal instability atop optical stability, dynamic internal activity atop quiet external appearance, and synchronized emissions within a rotating frame that shows no mechanical disruption. Each feature contributes to the growing realization that this interstellar visitor may represent a category of object not previously documented, one whose internal processes and material composition challenge established assumptions about small bodies entering the solar system from beyond. In the end, the story of 3I Atlas remains defined not by a single anomaly, but by the accumulation of many. Each observation, from synchronized emissions and thermal drift to trajectory stability and spectral irregularities, adds another point that challenges established expectations for interstellar objects. None of these features alone reshapes our understanding of small body dynamics. Yet together, they outline an object whose internal processes, material composition, and structural behavior are far more complex than the loose, fragile aggregates typically expected from beyond the solar system. Across months of monitoring, analysts tracked an object that maintained its structural coherence under conditions where most bodies fracture or disperse. It released material in coordinated pulses, resisted external forces, redistributed heat internally, and revealed chemical signatures that emerged only during specific energetic events. Surrounding halos formed and dissolved with geometric precision, while the surface reflectivity remained nearly unchanged through repeated cycles of activity. These combined observations do not point toward a simple explanation. Instead, they suggest that 3I Atlas represents a type of interstellar visitor not yet fully understood, one shaped by processes that do not fit neatly within existing cometry or asteroidal categories. Whether the driving mechanisms involve layered subsurface reservoirs, consolidated crustal structures, or deeper internal dynamics remains unknown. The forthcoming high-resolution imagery will determine how much of this behavior is linked to physical architecture and how much arises from internal conditions that cannot be directly observed. For now, 3I Atlas stands as one of the most intriguing interstellar objects ever documented, stable yet active, internally dynamic yet externally quiet, and governed by patterns that hint at an underlying complexity not captured by standard models. Its passage through the solar system offers a rare opportunity to expand the boundaries of our current frameworks, and to recognize that not all interstellar visitors follow the paths or processes we expect. As 3I Atlas moved farther from the inner solar system, slipping beyond the optimal range for detailed observation, the focus of the scientific community shifted from measurement to interpretation. The final datasets captured only the fading tail end of its activity, offering no definitive closure. Instead, they opened a new phase of inquiry, one centered not on what the object was doing, but on what its behavior implied about the population of interstellar bodies traversing our region of space. The question now facing analysts is whether 3I Atlas represents a rare anomaly or the first identifiable member of a broader, previously unrecognized class of interstellar objects. If the latter is true, it would suggest that the galaxy contains bodies far more structurally cohesive, internally organized, and dynamically active than current models predict. Several observatories have already begun reprocessing archival data in search of past candidates that may have been overlooked. Early findings indicate that at least 2 historical detections, previously dismissed as sensor artifacts or misclassified comets, might share subtle traits with 3I Atlas, faint halos with structured geometry, persistent albedo stability, and unexplained thermal fluctuations. While these records are incomplete and lack the coverage obtained for 3I Atlas, they introduce the possibility that such objects have passed through the solar system before, unnoticed due to lack of sustained observation. More importantly, research teams are now re-evaluating the assumptions used in interstellar object modeling. The standard framework, built on loosely aggregated material drifting between stars, may account for a large portion of such bodies, but not all. The existence of even a small population of structurally cohesive, internally active interstellar objects could reshape multiple fields of study, from planetary formation models to the physics of deep space material consolidation. This shift has already sparked new theoretical work. Some researchers propose that such objects form in high-energy regions near stellar remnants, where intense radiation and pressure could fuse material into dense, layered structures. Others suggest formation within long-lived protoplanetary environments, where subsurface heat and pressure might persist for millions of years, imprinting internal channels and reservoirs before the object is ejected into interstellar space. These models remain speculative, but they highlight a crucial point. 3I Atlas has expanded the theoretical landscape. The object's behavior suggests pathways of formation and internal dynamics that had not previously been considered or were dismissed as improbable. The idea that interstellar space might contain organized, resilient bodies with complex thermal and structural properties is no longer a fringe hypothesis. With observation of the object now limited to low-resolution tracking, the next stage depends on future detections. Astronomers are revising survey strategies to identify similar objects earlier in their inbound trajectories, when detailed high-resolution imaging is still possible. Enhanced infrared scanning, deeper time domain surveys and automated pattern recognition systems are being deployed to catch the next anomaly before it leaves the observational window. Until such an object appears, 3I Atlas remains both the first and the only representative of what could be a new category. Its brief passage has raised questions that extend far beyond the specifics of its structure. It challenges long-held assumptions about how matter organizes in interstellar environments and how much complexity can arise far from any star. What comes next depends on what the sky reveals and how prepared we are to look for it. In the months following the departure of 3I Atlas, the search for its successors intensified. For the first time, observatories around the world began operating under a unified framework designed explicitly to detect objects with similar behavioral signatures. This coordinated effort emerged from a growing realization. If 3I Atlas was not an outlier, then the solar system may serve as a passageway for interstellar bodies far more complex than previously imagined. The new detection strategies differ significantly from traditional comet search methods. Rather than relying solely on optical brightness or tail formation, astronomers now monitor for subtle secondary indicators: thermal instability, uncorrelated outflow patterns, and reflectivity anomalies. These traits, once considered noise, have become early flags for identifying objects that embody the same internal complexity seen in 3I Atlas. Advanced infrared surveys have taken on a central role. Interstellar objects with consolidated surfaces and internally regulated temperatures can appear unexpectedly dim in visible light, yet stand out clearly in thermal wavelengths. To capitalize on this, several research teams are deploying algorithms capable of identifying faint, irregular heat signatures that traditional comet hunting methods would miss entirely. Another transformation involves the way orbital data is processed. Instead of assuming that deviations from predicted gravitational paths are computational errors or outgassing artifacts, analysts now evaluate such deviations for deeper meaning. A small, consistent trajectory shift, the same kind observed in 3I Atlas, is now treated as a possible indicator of internal structural transitions or complex mass distribution. This shift in methodology has already produced results. Preliminary reviews of archival sky surveys uncovered a handful of objects whose brief appearances share characteristics once overlooked. One record, logged 20 years ago and dismissed at the time as an anomalous image streak, shows faint signs of structured halo formation. Another dataset contains an object with stable reflectivity across multiple solar angles, despite evidence of low-level activity. While the data are too incomplete for definitive conclusions, they reinforce the idea that 3I Atlas may not be unique. To support future analysis, observatories are developing predictive models that incorporate the new behavioral categories. These models explore scenarios involving consolidated crusts, stratified subsurface layers, and internal networks capable of channeling energy in non-linear patterns. Early simulations suggest that objects with such features could form in a variety of environments, from the accretion zones of young stars to the turbulent outskirts of planetary systems undergoing gravitational instability. At the same time, the global collaboration prompted by 3I Atlas has inspired new mission concepts. Several proposals outline small, agile spacecraft equipped to intercept fast-moving interstellar objects. These interceptors would not land or attempt prolonged study. Instead, they would perform rapid flybys, capturing high-resolution imaging, spectroscopic data, and thermal readings before the objects accelerate beyond reach. For objects that exhibit structured emissions or anomalous thermal behavior, such missions could offer the first opportunity to directly observe the architecture behind their activity. For now, the scientific community operates under a guiding assumption: the next 3I Atlas could appear at any time. And when it does, the infrastructure built in response to the first anomaly will be ready to capture data long before the observational window closes. Whether the next visitor confirms the patterns observed in 3I Atlas or introduces entirely new complexities, each discovery will contribute to a growing understanding of interstellar matter and the environments that shape it. This shift marks a turning point. No longer is the solar system viewed as an isolated system occasionally brushed by random debris. Instead, it is becoming a dynamic crossroads where diverse interstellar objects pass through, each carrying clues about distant regions of the galaxy and the processes that govern them. As research teams expanded their theoretical models, a central question emerged. What environments could produce an object with the internal organization and structural coherence displayed by 3I Atlas? Traditional cometary formation, shaped by slow accretion of dust and ice, could not account for the layered subsurface pathways, synchronized emissions, or consolidated crust inferred from the observational data. This discrepancy led to a new wave of hypotheses about the environments that might give rise to such bodies. One proposed origin involves the outskirts of protoplanetary disks, regions where heat and pressure fluctuate unpredictably during early system formation. In these zones, rapid temperature swings and turbulent flows could compress mixed materials into dense, stratified structures. Over prolonged periods, subsurface reservoirs might form naturally, sealed beneath layers of compacted dust and higher density minerals. If such an object were later ejected from its parent system, it could retain the internal complexity observed in 3I Atlas. A second hypothesis centers around interactions with stellar remnants. Near white dwarfs or neutron stars, the radiation environment is intense enough to fuse volatile materials into hardened crustal layers. Objects formed or processed in such environments could develop outer shells more resilient than those of conventional interstellar debris. These shells might channel or trap internal volatiles, producing the controlled emission pathways detected during 3I Atlas's passage. Another model examines the role of gravitational tides in densely packed star clusters. If an object crossed regions where gravitational forces shifted rapidly, such as the periphery of a young stellar nursery, internal layering could be compressed and reshaped over time. These repeated cycles of gravitational stress might produce deep fissures, vents, or subsurface networks capable of guiding future emissions. These hypotheses remain speculative, but they share a common implication. The galaxy may contain a much wider variety of small body architectures than previously recognized. The physics of interstellar material may not be limited to loosely aggregated ice and dust. Instead, some objects may emerge from high-energy environments, structured under conditions rarely seen in the solar system. This dramatically expands the scope of what interstellar objects can teach us. Every visitor becomes a potential probe, not of our own system, but of the environments where it formed. Their internal chemistry, structural resilience, and emission behavior may encode information about distant stars, exotic radiation fields, or early stages of planetary formation. In response to these possibilities, researchers are now developing classification frameworks based not on simple criteria like brightness or orbital eccentricity, but on deeper behavioral signatures, thermal irregularity, compositional stratification, structural coherence, and jet coordination. These attributes suggest that interstellar small bodies can no longer be grouped under a single umbrella. Instead, they may represent a spectrum of formation histories, physical conditions, and gravitational influences. As this framework evolves, analysts are beginning to re-examine known interstellar objects through a new lens. Even sparse or incomplete observations from decades past are being reassessed for hints of structured activity. Early results show that faint traces, once dismissed as observational errors, could be early indicators of overlooked complexity. This growing body of evidence has ignited a new scientific ambition to create, for the first time, a galactic catalogue of interstellar object types. Instead of treating such objects as anomalies, researchers are preparing to map their diversity, origins, and physical behaviours systematically. If successful, this catalogue would offer unprecedented insight into environments far beyond the reach of any spacecraft. For now, the clues provided by 3I Atlas serve as the first entries in this new field of study, a reminder that the solar system is not isolated and that its brief visitors can reveal stories written in distant corners of the galaxy, as researchers expanded their models to include structured, internally active interstellar objects. Attention gradually shifted toward the potential risks such bodies could pose. While 3I Atlas itself never approached Earth closely enough to raise immediate concern, its behavior introduced scenarios that existing planetary defense frameworks were not designed to address. Traditional risk assessments rely on predictable responses to gravitational forces and sunlight-driven outgassing. But an object with internal pathways, layered subsurface reservoirs, and consolidated crustal structures may not behave as expected. Its activity could shift without external triggers, altering its path in subtle ways that make precise predictions more difficult. Analysts now recognize that trajectory models must account not only for solar influence, but for internal mass shifts, pressure buildup, or thermal redistribution. One particularly challenging possibility involves objects capable of rapid emission bursts, similar to those observed in 3I Atlas. If such a burst occurred during a close approach to a planetary body, the resulting non-gravitational acceleration could redirect the object by a measurable margin. Even minor changes in direction, fractions of a degree, could significantly alter impact probabilities. This introduces a new layer of uncertainty into the evaluation of interstellar objects passing near Earth's orbit. Another concern centers on the structural resilience of these objects. Most known comets can fragment under thermal stress or gravitational interactions, reducing the threat they pose. But an object with a hardened crust or internally reinforced matrix may resist fragmentation even under extreme conditions. If such a body were on a collision course with Earth, standard deflection strategies that rely on breaking the object apart might prove ineffective. Orbital analysts have begun modeling scenarios in which a compact, dense, internally active interstellar object approaches Earth. These simulations reveal that small deviations in emission timing or pressure wave propagation inside the object could complicate interception strategies. Unlike typical debris, which follows relatively predictable heating and cooling cycles, an object with subsurface networks could respond unpredictably to external stimuli, including attempts to redirect it. Beyond the physical risks, there are observational challenges. Objects like 3I Atlas may not display conventional visual signatures until they are relatively close to the Sun. Their consolidated surfaces can limit dust production, making them harder to detect at long distances. If such an object entered the solar system on a trajectory aligned with the glare of the galactic plane, or approached from the direction of the Sun, it could remain unseen until late in its inbound path. To address these concerns, planetary defense agencies are pushing for broader sky coverage and deeper early warning capabilities. Infrared detection arrays, capable of spotting thermally inconsistent bodies long before visible activity emerges, are being prioritized. In addition, rapid response telescopes are being developed to track structural shifts and emission events in real time, allowing analysts to adjust trajectory estimates with far greater precision. Despite these concerns, researchers emphasize that the risks remain theoretical. No structured interstellar object has been observed approaching Earth on a hazardous trajectory. Yet the mere possibility has prompted a reassessment of how planetary defense systems classify and respond to interstellar bodies. At the same time, these risks highlight a broader opportunity. Understanding objects like 3I Atlas may not only improve planetary defense, but also deepen our understanding of galactic environments. The internal coherence, emission patterns, and thermal anomalies observed in such objects may encode information about formation processes that occur far from any star. In this sense, the risks and the scientific potential are intertwined. As research continues, a new paradigm is emerging. Interstellar objects are no longer rare curiosities. They are active participants in the dynamic environment of the solar system, each carrying with it the fingerprint of a distant, unknown origin, and the possibility of behavior that challenges even our most advanced predictive models. As the implications of 3I Atlas became clearer, space agencies and research groups began outlining a new class of exploratory missions designed specifically for encounters with interstellar objects. Until recently, such missions were considered impractical. Interstellar bodies often travel too fast, appear too late, and depart too quickly for conventional spacecraft to intercept. But the unusual behavior of 3I Atlas, and the possibility that similar objects may follow has shifted the conversation from if to how. The new mission concepts focus on rapid deployment, modular design, and autonomous navigation. Unlike traditional planetary probes that require years of planning and carefully optimized trajectories, these interceptors are built for responsiveness. Their purpose is simple: launch quickly, approach the object during its inbound path, and gather high-resolution data before it accelerates beyond reach. One proposal involves a fleet of small, fast spacecraft stationed in heliocentric orbit. These vehicles would remain dormant until an interstellar object is detected. Then, using high-efficiency propulsion systems, they would maneuver to intercept the object at high relative velocity. Even a brief flyby, lasting minutes or hours, could provide imaging and spectroscopic detail far exceeding what Earth-based telescopes can capture. To handle objects with irregular or unpredictable activity, the interceptors are designed with wide-spectrum sensors capable of detecting subtle thermal changes, electromagnetic anomalies, and micro-emission signatures. These systems would allow the spacecraft to adjust their trajectories in real time, avoiding hazardous outflows while maintaining data collection. Another mission concept focuses on deploying lightweight probe swarms. Instead of relying on a single spacecraft, dozens of microprobes would approach the interstellar object from multiple angles. This distributed approach reduces risk. If a few probes fail due to sudden emissions or thermal spikes, others can continue gathering data. The swarms could map temperature gradients, detect subsurface structural patterns, and identify the geometry of vents or crustal fractures, all within a short observational window. Researchers also envision missions capable of trailing an interstellar object after perihelion, collecting data as it exits the solar system. This strategy could reveal long-term changes in rotational stability, emission decay, and surface evolution. Although the outbound phase offers less opportunity for detailed imagery due to reduced sunlight, it provides invaluable information about how internal processes behave as the object cools and recedes into deep space. Even more ambitious are proposals to deploy interceptors into interstellar trajectories themselves. These craft would not return or remain local to the solar system. Instead, they would accompany the object into interstellar space, studying its long-term structural evolution far beyond the Sun's influence. While technically challenging, such missions could offer unprecedented insights into the materials and physical processes shaping distant regions of the galaxy. The motivation behind all these mission designs is clear. 3i Atlas demonstrated that interstellar objects can carry signatures of internal organization far beyond what telescopes alone can reveal. Direct observation, close enough to detect microfractures, thermal vents, or chemical layering, is the only way to determine whether these objects are shaped by processes that cannot be inferred from remote data. For now, these concepts remain in exploratory stages, but the rapid pace of development reflects a growing recognition that future interstellar visitors will not be ignored. With new detection infrastructure in place and mission plans forming, researchers expect that the next anomaly will not slip away unexamined. When the next interstellar object enters the solar system, humanity may be ready not only to observe it from afar, but to meet it directly, carrying instruments capable of revealing the structures, materials, and histories hidden beneath its surface. In the wake of 3I Atlas, a new scientific landscape has taken shape. What began as a single anomalous encounter has evolved into a broader redefinition of how interstellar objects are detected, interpreted, and understood. The behavior of 3I Atlas, its synchronized emissions, internal thermal migration, structural resilience, and persistent reflectivity revealed that the diversity of bodies crossing the solar system may be far greater than previously assumed. The response to this revelation has been equally transformative. Researchers have shifted from passive observation to targeted, proactive search strategies. They now look for subtle thermal signatures, unconventional trajectories, and structured outflow patterns that once blended into background noise. These new detection methods have already uncovered hints that similar objects may have passed through the solar system before, unnoticed or misclassified due to the limitations of old frameworks. At the same time, advanced mission concepts, rapid interceptors, distributed probe swarms, and deep space trackers have emerged as essential tools for uncovering the internal architecture of future interstellar visitors. These missions reflect a growing recognition that remote observations alone cannot fully capture the complexity of objects shaped by distant, unknown environments. Together, these developments point toward a new era of discovery. Instead of treating interstellar objects as rare, unpredictable anomalies, scientists are preparing for a steady influx of visitors whose structural and compositional diversity may serve as a direct window into the conditions of star-forming regions, high-energy stellar remnants, and gravitationally turbulent clusters scattered across the galaxy. The journey of 3I Atlas through the solar system was brief, but its impact on scientific thinking has been profound. It expanded the boundaries of what small interstellar bodies can be, challenged long-standing assumptions about their formation, and inspired a global effort to detect and study their successors with unprecedented precision. As the next object approaches, whether months, years, or decades from now, humanity will be better equipped than ever to recognize its signatures, interpret its behavior, and uncover the story it carries from the distant regions of the Milky Way. The path forward is clear. Every interstellar visitor is an opportunity, and each one may reveal something new about the galaxy that surrounds us.